Good afternoon. So this is going to be your asynchronous version of the lesson where we're going to be learning about energy level diagrams, valence electrons, and Lewis dot diagrams. 3 learning targets here. 1, you're going to be able to draw energy level diagrams by the end of this video for the first 3 periods of the periodic table. 2, you're going to use those energy level diagrams to identify valence electrons and oxidation numbers, also core electrons. Lastly, you're going to be able to write and name simple ionic compound formulas using those oxidation numbers. So let's get started. So there are a total of 7 energy levels where electrons can live inside of an atom. And ironically enough, if you take a look, you will notice that there are 7 rows or periods of your periodic table. So anything in period 1 has 1 energy level. So hydrogen and helium are the elements that will only have 1 energy level. In contrast, if I look down at cesium, number 55, it's going to have 6 energy levels. And we're going to explain what an energy level actually means in a moment. So notice at the bottom here, you've got a couple of asterisks marks here. So that first asterisk means that it's the lanthanide series that is broken out between 57 and 72 in period 6. So all of these 58 through 71 also have 6 energy levels. And in period 7, where these 2 asterisks are, is your actinide series. So between 90 and 103, those are going to have 7 energy levels. So as aforementioned, since hydrogen is in the first row, first period, hydrogen has 1 energy level. Lithium is in period 2, so it has 2 energy levels. And I challenge you to think about how many energy levels will there be in magnesium. I'll give you a hint. So it's important to know that in a neutral atom, the atomic number, and we reviewed this back in December, I believe, a neutral atom equals the same as the number of protons, which is also going to be the same as the number of electrons. So example, hydrogen has 1 proton, and in a neutral atom, it's also going to have 1 electron. Lithium has 3 protons, so in a neutral atom, it's also going to have 3 electrons. Magnesium has 12 protons, and in a neutral atom, it will have 12 electrons. That's something important to remind yourself of as we move forward. So we're going to introduce what we call the Bohr's model diagram. In a Bohr's model diagram, we can model where electrons will live inside of an atom. And in a Bohr's model diagram, energy levels are modeled with circles. So I'm going to give you a list of 4 attributes of a Bohr's model diagram, and then of course we're going to draw a couple. So in a Bohr's model diagram, we're going to draw a dark circle in the center that's going to represent the nucleus of an atom. Important rule here, the first energy level can only hold 2 electrons. The first energy level can only hold 2 electrons. We're not going to get into why that is, just accept that as a fact. The second and third energy levels can hold a total of 8 electrons. We're not going to go above the third energy level this year. So just remember that the first energy level can hold 2 electrons. Second and third energy levels can hold 8 electrons each. So here's our example. So let's draw a Bohr's energy model diagram for hydrogen. I'm going to start by drawing my dark dot in the center to represent the nucleus. I'm going to very easily draw a circle around that dark dot. That represents energy level 1. And hydrogen has 1 electron. I read that directly off the periodic table. So I'm just going to put a dot in the first energy level. So if you're a fan of the Watchmen like I am, you'll know that Dr. Manhattan has that symbol. tattooed on his forehead. Let's do this for magnesium. Magnesium has a total of 12 electrons, so we're going to have more energy levels going on here. And we also know that magnesium lives in energy level 3. So we are going to have 3 rings around the nucleus. There's ring number 1, first energy level. Ring number 2, second energy level. Ring number 3, third energy level. Now we're going to fill up those energy levels. So there's going to be a total of 12 electrons inside of the magnesium. So remember the rule is that the first energy level can only hold 2. So I'm going to put 2 here, 1, 2. And I always go top, bottom first, and I don't put them together. And there's a reason I don't do that I'll explain later. So that first energy level has 2. First energy level is now filled. So I'm going to move up to the next energy level, which holds 8. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. So now I've found homes for 10 out of 12 of my electrons. So I'm going to just add the last 2 to the third energy level. And there is my Bohr's model energy level diagram for magnesium. All right, so let's talk about valence electrons. So here once again is the Bohr's model energy level diagram for hydrogen. So hydrogen has 1 valence electron and what we say no core electrons. We define valence electrons as electrons that live in the outermost energy level of an atom. So that 1 electron is in the highest energy level, so hydrogen has 1 valence electron. Hydrogen has no core electrons because there is only 1 electron, so it has to be the valence electron. Now here's magnesium again. And magnesium is going to have 2 valence electrons because we have 2 electrons that live in the outermost third energy level, that one that's going to be behind my notes here. So I have 2 valence electrons here, and everything else is on the inner energy levels of magnesium. So that means that there are 10 core electrons. The core electrons just basically hang out, don't do a lot of anything. The valence electrons are going to be what participates in ionic bonding. And those are the ones we really care about. So I can ask myself, how many core electrons and valence electrons does lithium have? I'll give you a moment to think about that if you're in class with me to answer that on your whiteboard. Or if you're at home, you can draw out the Bohr's model diagram for lithium, count the valence electrons, and count the core electrons. So one important question you might ask is, do you have to draw that Bohr's energy model diagram every single time you want to figure out how many valence electrons an atom has? The answer is no, you do not. All you have to do is you just have to look at the Roman numeral that appears by the A group elements on your periodic table. So you'll notice here that column 1 or group 1 is group 1A. That means everything in this column here is going to have 1 valence electron. This is group 2A, so they're going to have 2 valence electrons. We're going to skip this whole entire section here, this whole entire transition metal section, because they get a little complex and we're not going to get into it this year. Here's going to be group 3A with 3 valence electrons, group 4A with 4 valence, 5 valence electrons, 6 valence electrons, 7, and then the noble elements of them all are the noble gases, and each of those are going to have 8 valence electrons. Except for helium, which is only going to have 2. So the exception to that is helium, which has 2 valence electrons. So you can look directly on that periodic table and tell exactly how many valence electrons each one of those elements are going to have, neglecting the middle section because we're not going to get into that. So we're already at our second learning target, where we're going to learn how to draw Lewis dot diagrams as a way to represent the number of valence electrons in a particular atom. These are really, really simple to draw. If you know how many valence electrons are in a particular atom, and you can figure out the symbol from the periodic table, all you got to do is put some dots, and you're just going to put these dots in a diamond-shaped pattern around the symbol, and you're going to only pair them up only if you have more than 4. So I'm going to show you what I mean by that. So let's say I'm going to draw the Lewis dot diagram for hydrogen. I am going to look at my periodic table and realize that hydrogen has 1 electron and is in group 1, so it has 1 valence electron. Its symbol is H. So I draw H just like this. And it has 1 valence electron, so it's just that simple. There's the Lewis dot diagram for hydrogen. Now magnesium, we've already discovered it has 2 valence electrons, but we can also figure that out because it's in group 2. So 2 valence electrons for magnesium, and its symbol is Mg. So I write Mg and go north, south. So I do not pair those up, and I don't pair up electrons because electrons are negatively charged and repel each other. So they won't be living in the same orbital unless they have to. So I always put them apart from each other until I have to pair them up when I've got more than 4. So that's how simple it is to draw a Lewis dot diagram for any elements, A group elements on your periodic table. Okay, if you were in class with me in person, you would be doing this on your whiteboards right in front of you. At home, this is your time to check for understanding. You might have this in an Edpuzzle where you can share with me the picture of your work while you're doing this. So what you're going to do is on a piece of paper or a whiteboard, please draw the Bohr's model for each one of these, and then please draw the Lewis dot diagrams for each. And I'm going to pause for a moment and let you do that. And then when we come back, you can check your work. So hopefully this is what you saw for carbon. Carbon, you noticed, if you looked at your periodic table, has 6 protons and electrons in a neutral atom. And it is in period number 2, so it has 2 energy levels. So I'm going to draw a solid dot in the center representing the nucleus. Here's energy level 1. Here's energy level 2. And then I'm going to choose a different color here. I'm going to start by filling in all 6 electrons. 2 live on the first energy level. 4 live on the second energy level for a total of 6. And then to draw the Lewis dot diagram, the symbol for carbon is C, and it has 4 valence electrons, north, south, east, west. As long as you hit the 4 corners and they're not paired up, you're correct. Let's try the next one here. So sulfur, looking at our periodic table, is element number 16 and has 3 energy levels. So I'm going to put that dark circle in the center for the nucleus. First energy level, second energy level, third energy level. And then I'm going to fill in some electrons. I got 16 of them to do. The circles don't have to be perfect, obviously, because mine are very ugly. But here's the first 2. 2 electrons live in the first energy level. Then 8. 1, 2, 3, 4, 5, 6, 7, 8. That's a total of 10, so I have 6 more. So I go 1, 2, 3, 4, 5, 6. And 6 valence electrons are what I've got. So I go sulfur, 1, 2, 3, 4, 5, 6. 2 will be paired up and 2 will not be paired up. So now we're going to see why it's important to figure out how many valence electrons each of these atoms have. Here's a couple rules that are incredibly important for all of bonding and all of chemistry. One is that all atoms want to be like a noble gas, and they will either lose electrons to become like their closest noble gas, or they will gain electrons to be like their closest noble gas. Most elements, the goal is to obtain 8 electrons in their outermost shell to become stable. 8 is the perfect number in chemistry. We won't go into why, just trust that 8 is the perfect number. Some elements will like to lose 1 electron to be like helium, because helium will have 2 valence electrons. That's the exception to the rule. What I just described to you is what we call the Octet Rule. And the Octet Rule is everything wants to be like a noble gas with 8 valence electrons, or helium with 2 valence electrons, which is called the duet rule. So the Octet Rule is wants 8, and duet rule wants 2. So atoms are going to either give away electrons or take electrons to get those 8 or 2 electrons. And we can also call the energy levels shells. If an atom loses electrons to become like its closest noble gas, it's going to become more positive and become what we call a cation. Cat means positive, ion means it's lost electrons. If an atom gains electrons, it becomes more negative and it becomes an anion. An stands for negative, ion means gain or lose electrons. So if I take a look here at magnesium, here's the Lewis structure, or Lewis dot diagram for magnesium again. It has 2, and here's magnesium on the periodic table. You'll notice that magnesium can lose 1, 2 to become like neon. So magnesium is going to lose those 2 electrons. When you lose electrons, you become more positive because you're losing negative things. So we say that magnesium is going to end up having a charge of +2, which we saw before in one of the Build the Atom PhET simulations that we did earlier this year. And magnesium becomes that cation, magnesium +2. Whereas sulfur has 6 valence electrons, and here's sulfur here like this. Notice that sulfur can gain 1, 2 more to be like its closest noble gas, argon. So what's going to end up happening is sulfur is going to gain 2 more electrons. When you gain more electrons, you become more negative, and sulfur is going to end up having a -2 charge. So however many electrons an ion has to gain or lose to become like its closest noble gas is going to be what its charge will be, or we can also call that oxidation number. So now, as you can predict, since cations want to give away electrons and anions want to take electrons, when we got cations bonding with anions, it's a perfect match, and we call that an ionic bond. So here's your example of magnesium and sulfur once again. Remember that sulfur wants to gain 2 electrons. Magnesium wants to give away 2 electrons. So magnesium is going to give 2 electrons to the sulfur to make a total of 8. And I can draw this ionic bond with this particular model showing that sulfur has 8 and magnesium is paired with the sulfur so that there is a multiple of 8 in that ionic compound, making it stable. So that's going to be your ionic bond of magnesium and sulfur. And I'm just going to add in here how easy it is to name this. The name of this particular ionic substance is going to be magnesium. I'm going to write out the name sulfur here for a second. And then remind myself that when I'm naming an ionic compound, I drop the last syllable, and change it to IDE. So the name of this particular ionic compound is magnesium sulfide. Here's the example of aluminum and oxygen. Here's Al with 1, 2, 3. Here's oxygen with 1, 2, 3, 4, 5, 6. Getting those from the periodic table, looking at the number of valence electrons. This one's going to be a little bit trickier because you're going to have more aluminums and more oxygens that need to be bonded together in order to make these multiples of 8 valence electrons like a noble gas. So oxygen wants 2 more to make 8. So aluminum is going to give the oxygen 2, but now aluminum is kind of unhappy here because it has 1 left over. So another oxygen shows up, and since there's a large abundance of those in the universe, it's really easy to find one. Then I'm going to end up saying, all right, oxygen's going to take that 1 extra one from the oxygen, or from the aluminum. Now oxygen's unhappy. It's okay, I've got tons of aluminums with 3 valence electrons. So aluminum is going to give 1 more to the oxygen. And then we need 1 more oxygen to take the last 2 from the aluminum. So notice now I've got 8, 16, 24, a multiple of 8 valence electrons in this compound. There are 2 aluminums. So I'm going to say Al and a subscript 2. The subscript 2 means I've got 2 aluminums. And then I've got 3 oxygens, 1, 2, 3, Al2O3. Last but not least, to name this, I write out the cation, aluminum, and oxygen turns to oxide. So I make aluminum oxide. So that was a lot of information there, but that's okay. We're going to have some practice. So I wrote here for you that the number of ions in the compound is represented by the number in the subscript. So once again, if I've got Al2O3, I've got 2 aluminums, and I've got 3 oxygens. That's what that means. All right, so this might be a real pain to always do the ionic compound using the Lewis dot method. So I'm going to show you an easier way to do it using just the oxidation numbers. So here's magnesium. Now magnesium wants to lose 2, so it has a +2 charge. Sulfur wants to gain 2, so it has a -2 charge. The goal in any ionic compound is for the oxidation numbers to add to 0. Well, in this case, it's really simple. +2 - 2 equals 0. That means I only need 1 magnesium to every 1 sulfur. I don't necessarily need to write those particular subscripts, but sometimes it's handy to know that means 1 magnesium, 1 sulfur, which is the same thing as saying MgS. Aluminum and oxygen, a little bit trickier. I have aluminum with a +3 charge, wants to give away 3. Oxygen with a -2. So I have to think to myself, what can both 3 and 2 go into in order to figure out how many electrons are in the total substance? So I could say multiply 3 times 2, which gives me 6. 3 goes into 6 2 times. 2 goes into 6 3 times. So I'd have 2 aluminums for every 3 oxygens. Or another really tricky way of looking at this is look at the charges, make them subscripts. Flip the charges, make them subscripts. The 2 can go with the aluminum, the 3 can go with the oxygen. Al2O3. And the charges don't carry down because we're looking for how many ions, not the number of electrons it gained or lost. All right, so that was the end of the information for finding out how many valence electrons a particular ion has, how to draw Bohr's energy models, how to identify the oxidation number or the charge of each of the ions, and how they match together to make simple ionic compounds, and a little bit of naming them. So you're going to have a practice attached to Schoology that if you're in class with us, you can just do either on a whiteboard, show me, and I'll put it in Schoology, or if you're at home, you can do it on Kami. Thank you for making it to the end of this video.